Number 92. Draw the heating curve that is observed when ice is warmed from negative 20 degrees Celsius to 120 degrees Celsius. Which sections of the curve correspond to the molecular art in A, B, and C? So heating curves are interesting graphs, and to draw one properly, you need to know the specific heat of the substance that you're dealing with, which is water. So here's the specific heats of solid, liquid, and gaseous water. You can see from the specific heats that the liquid water requires the most energy to warm up. Now, when you raise water from negative 20 to 120 degrees Celsius, you're going to pass through all three phases. When you start at negative 20 degrees, that's going to be solid water, and when you end up at 120, that'll be gaseous water. So you're going to pass through all three phases. So as you warm up water, when it's a solid, it's going to cost you this many calories per gram to warm it up 1 degree. And when you get to a liquid, it's going to cost you that many calories per gram to warm it up 1 degree. And then when you finally get to a gas, it's going to cost you that many calories, per gram per degree. Don't forget that when solids convert into liquids, there is an extra amount of heat that's required. So when you do phase changes, like the melting and also the boiling especially, it's going to require an extra amount of energy. And for melting, it requires 79.7 calories to melt 1 gram. And for boiling, it's a lot more, 540 calories per gram. So taking all this information into account, okay, this might be a little bit more than what the author is looking for. I think if you look at the heating curves in the textbook, they might not be as accurate as this one. So this one, we're going to, put it out a little bit more accurately. If you draw the heating curve on the y-axis, it's going to be temperature in degrees Celsius, and so 0 Celsius, 100 Celsius, and so this will be 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Then you're going to have 110, 120. So this is where you're going to end up. And then going back to 0, this will be negative 10, negative 20. This is where you're going to start off. Okay? So you're going to go all the way from here to here. And it's going to take you a certain amount of heat, and that's going to be on the x-axis. So heat is listed on the x-axis. We'll just leave that scale off. Okay, so we're not going to draw a scale here, but you could if you wanted to. It's not really necessary for this problem. So if you have a substance and you're starting at negative 20 degrees Celsius, okay? So before you add any heat, you're right here, and it's at negative 20 Celsius, you're at a solid substance, okay? That's going to be this picture right here. I think I got these letters backwards. So this should be B, and that should be A right there. Sorry about that. So B and A. So the solids have a nice ordered structure. So that's a solid right there. Okay, so if you're at negative 20 and you start adding heat, solids have a pretty small specific heat compared to liquids. So if you add a little bit of heat, it's going to jack up the temperature really quick. The slope of this line is pretty steep. And then you're going to get up to 0 degrees. So it's ready to melt. But before you get to a liquid, you have to add the energy required to melt it. And that's going to be from from the heat of fusion. It costs 79.7 calories per gram. Okay, so it's gonna cost quite a bit of energy to melt it. So as you melt a substance, the temperature remains constant, so flat line. And then after it's all melted, you now have a liquid. You're ready to raise the temperature again. But this time, the heat that you add, it warms it up more slowly. Look at the slope of this line. It's not as steep as that one. Okay, this one, you add a little bit of heat, it jacks up the temperature. This one, you add a little bit of heat, the temperature doesn't go up as much. And that's because it costs more energy to raise the temperature of a liquid than that of a gas, or a solid, really. Solids and gases have about the same specific heat. So the slope of the liquid curve is more shallow than the slopes of the gas and the solid curve. Okay, so you add some heat. It takes quite a bit of heat to raise the temperature of a liquid up to the boiling temperature. Then when you finally get up to the boiling temperature of 100 degrees, it's going to take a lot of energy to boil, because boiling requires 540 calories per gram. So it takes a lot of energy to boil. And then once all of that energy has been added, it's now in the gas phase, and just a little bit more energy warms up the gas to 120 degrees, because the gas has a pretty small specific heat. Now this graph isn't quite drawn to scale. If we were to do this accurately, the horizontal melting line would stretch way out to here, and then the boiling line would be even further. We'd need a really long graph, and it's just more than I could fit on this paper, but you kind of get the picture. The slopes of the lines for the solid, liquid, and gas are pretty accurate. The liquid has a more shallower slope. I think the slopes of the lines being taken into account, as they correspond to the specific heats, is a little bit more than the author was looking for in this problem.